Today we're going to continue studying the relational data model. And before we start the lecture, I first want to let you know that the first assignment is posted on the blackboard under the assignment folder. So if you go to the content under the assignment folder, and also if you notice that I actually extend the deadlines from February, I think 13 to 18. So I think today and the next class, we're supposed to wrap up the relational data model. So then I think you're able to work on all the questions. Actually, we only have 2 questions in this assignment. So then I think you should be ready to work on your assignments. So now today, we're going to continue studying the functional dependency. So we know the functional dependencies are actually describing the relationship between the 2 sets of attributes. So I think in the last class we kind of studied what is functional dependency, how to examine the functional dependency given a table. Okay, so once again, in this class, we mainly focus on the functional dependencies whose attributes are from a same relation schema. Okay, so the dependent on the right-hand side and determinant on the left-hand side, they are actually from the same, from the same relation schema. So also in practice, we may have functional dependencies whose attributes spread out on different relation schemas. Then in this class, we do not consider those functional dependency. Okay, now let's study some rules called splitting and combining rule of the functional dependency. So the splitting rule, I think we have discussed before already. So for example, given a set of attributes as determinant and a set of attributes as dependent, we can split this rule into a set of rules. So basically, we keep the determinant, but we just put a single attribute as dependent on the right. Okay. So for example, originally we have m different attributes on the on the dependent side. Then we can convert it into m functional dependency. They all share the same determinant, but their dependent, has only one attribute. Okay, so this is called splitting rules. Okay, means that if you have multiple attributes on the dependent side, then you can split them into multiple separate rules. The combining rules is basically a reverse process. So given a set of functional dependencies, they all share the same determinant and their dependent side only has one attribute. Then we can merge all those rules together as long as they have the same determinant on the left. Then we simply combine or merge the dependent all together. Then we come up with more kind of composite rules. Okay, so that's called splitting and combining rule. So given functional dependency, whether we want to split it, or whether we want to combine it with some other rules, I think that's really depending on the application. Okay, so the needs. Okay, so depending on the needs, you may want to use the merging rules. So you replace multiple rules with a single rule. That's more kind of concise. Or sometimes you want to do like the calculate the closure of a set of attributes. You may want to split a long rule into smaller rules. Then you can help you to identify the closure of a certain set of attributes. Okay, so that's called splitting and combining rule. The second one, we also discussed some other types of functional dependency. Here, it shows 2 types. One is called trivial functional dependency. So trivial basically means that the dependent is included in the determinant. In other words, dependent is a subset of the determinant. So if the rule like this kind of pattern, then this rule is called trivial functional dependency. And then here give you one example, like customer name, customer address, determine customer name. So the customer name is actually one attribute of the determinant. So one of the attributes in the determinant. So this rule is considered trivial because the dependent is included in the determinant. So it means that it's always true. Okay. Default functional dependency, I think we also mentioned in the previous classes. So basically it means that given a relation schema R, if K is the key of the relation R, then K, this key functionally dependent, determine all other attributes of R. Okay, so that's called default. So by default, that is true. The reason it is true because a key can be used as an identity for each record in a table. So given a valid key, we have only one record corresponding to that key, then we're able to retrieve all the other attributes value. So that's why this is considered as default functional dependency, means a key determines all other attributes of the same relation schema. Okay. And here give you one example. Given the student relation schema, if T number is considered as a primary key, is also key, then T number determines name, email, address, and major. Okay. Okay, let's go to the next one, the closure. So this is a kind of the very important concept of the relational data model. Okay, so whenever we have a set of attributes, so given a set of attributes and a set of functional dependency, so we use S to represent the set of functional dependency, then we can calculate the closure of A1, A2, all the way to the AN under this functional dependency. So this closure is defined as a set of all attributes that are functionally dependent on the A1, A2, or AN. In other words, the closure really identifies, given a set of attributes and a set of functional dependency, the closure of that set of attributes really determine or really decides the attributes that can be derived or determined by the set of attributes. Okay. So we use a special notation like superscript plus, given the set of A1, A2, or AN, then curly braces indicate the set of attributes. Then outside of the curly braces, we use this super plus to indicate the closure of A1, A2, all the way to the AN. Okay. And also, given the A1, A2, AN, and the set of attribute, a set of the functional dependency, we know that the A1, A2, AN themselves will belong to the closure because that's trivial functional dependency. So a set of attributes determine itself. Okay. Then the closure of attributes usually is used to define or identify the key of a relation. So this might be possible that, for example, you are not given a database, each table should have a key. And since you are not the designer of the database, you might not know if what attributes make a key for a given relation schema. Then if you know the functional dependencies, then you probably can calculate every possible and the closure of every subset attributes of whole relation schema to determine if a subset of attributes can make the key of that relation schema. So let's we will discuss that later in some examples. So this slide shows how we calculate the closure of a set of attributes. So basically, in order to calculate the closure, we first have a set of attributes, and also we need to have a set of a functional dependency. So in the extreme case, if we only have a set of attributes, but we do not have any functional dependency, then the closure of that set of attributes will be itself. So it basically means that we don't have any more attributes be added to the closure, because if we want to have more attributes to be added to that closure, then we have to have the functional dependency, and we can say if there's any attributes that determined by the set of attributes, set of the attributes that we try to calculate the closure. Okay. So here I give you the algorithm. So this algorithm is very simple. For example, first, for all the functional dependency in S, if possible, we're going to split the functional dependency. So the purpose of the split is that we're going to end up with a set functional dependency that only has a single attribute as a dependent or in the dependent. Okay, so that's make us kind of calculation maybe more much easier. Okay, so recall that split rule. What we're going to do that we just simply keep the determinant and change. We just put one attribute at a time in the dependent to make a set of separate rules. Okay, and then so first we have to split the rules in the functional dependency. Then we use a capital X to say the closure of the attributes. And then we initialize X to be the A1, A2, AN. So that's that attributes whose closure we want to calculate. Okay. Then we repeatedly search for some functional dependency in S. So, for example, B1, B2, Bm determines C, such that the B1, B2, Bm is actually included in either, included in X, because this X will be constantly updated during the calculation process. So the X initialized as A1, A2 to the AN. So maybe the first step, we need to find a functional dependency whose determinant is a subset of the A1, A2, AN. Okay, then we add, for example, if B1, B2, Bm is a subset of the original set of attributes, we add C to the X. Now the X contains A1, A2, AN plus C. Okay, then we're going to examine if there's any functional dependency in the set whose determinant is included in the X. Then we're going to add the dependent to the X. So we're going to repeat this process until we will not be able to add any attribute in this closure X. Then we stop. So then whatever we have, the attributes in the X will be considered as the closure of the A1, A2 to the AN. So let's see the example here. Okay. So assume that we have a relation. Okay. So R contains 6 attributes, and also we have set of functional dependencies. So we have A, B determines C, A, B, C determines A, D, and D determines E, and CF determines B. So maybe I want to duplicate this one so that we can do the calculation. So according to the algorithm, actually we have to split the rules. So I think A, B determines C cannot be splittable because we only have a single attribute on the dependent side. But the B, C determines AD will be revised by 2 functional dependency. BC determines A and BC determines B. Okay, so this is called splitting. So maybe this is not good. I don't want to get confusing. So. Okay, so this kind of splitting rules. So the first time we're going to apply, sorry. Apply rule splitting. Splitting. Okay, then we come here. So I think only this BC determines AD will be splitted because for the remaining rules, we only have a single attribute in the on the dependent side. Okay, so once we have these rules, so now we have AB determines C, BC determines A, BC determines D, and D determines C, and CF determines B. Okay, now I think we start with AB because asking us to calculate AB. So we initialize the closure as AB, okay? Then we can apply because I don't know if so this initialize as AB, okay? Then we're going to apply AB determines C. So now since AB is included in the NB, so that's why we're going to use AB and also put the C into the closure. Okay? Gosh. I'm sorry, I think this room is so dark. The lights keep shutting off. Come on. Looks like I need to walk around in order to keep the lights on. Okay, so this is the first step. Okay, now we have closure ABC. Then we go back to the functional dependency to see if there's any functional dependency whose determinant or the left-hand side attributes can be found in this closure. So I think now we can, for example, BC, okay? Yeah, BC is included here, okay? So now we can apply the BC. Then, because BC determines A and the BC determines D. So given the BC here in the closure, apply BC determines A and the BC determines D, then we're going to have basically add A and D. Okay, so we start with this one, then we add A and D to the closure. Since A has already been here, so that's why we do not need to add A again. We just add the D. Okay, so we can use adding. Okay, since A has already been in the closure, so we do not need to add A back to the closure again. We just need to add the D, which is not in the original closure yet. Okay, now we have A, B, C, D. Now we're going to go examine the other functional dependency if their determinant is included in the A, B, C, D. Apparently D determines E because D is here, so we apply D determines E and then add the E to the closure. Now we have A, B, C, D, E, okay? And then although we have C, F determines B, we do have C in the closure, but we do not have F. Okay, so that means that given this set of functional dependency, then the closure of AB will be the A, B, C, D, E. Okay, so then kind of back to the comment that we said that the closure of attributes can be used to find a key of a relation. Okay, so what is a key of a relation? So key basically of relation basically means that given a set of attributes and given a set of functional dependency, if the closure of this set of attributes include every attribute of the relation, then the the set of attributes is considered as a key. Okay. So in this case, we can tell that AB's closure contains A, B, C, D, E, but not all attributes in R. So that means that AB cannot be the key of the relation R. However, if we add one more attribute, F, now F was originally is missing in the closure of the AB. Okay, so if we add this attribute F into the set, now the story will be changed. So basically, means ABF will basically, I think I put it wrong. The closure will be the all attributes of the relation. So contains every attribute of the relation. So you can examine it because it will be A, B, C, D, E, because that's coming from AB closure. So once we have the A, B, C, D, E, then if we consider F into it, then it has everything. Okay, has all attributes in the relation schema. So in this case, ABF is considered as the key of the relation R. The reason its closure contains every attribute. Okay, so I want you to know that when we calculate the closure, we can calculate any set of attributes of a relation schema, calculate the closure of them. So there's so many closures we can calculate besides AB's closure. So we can calculate, for example, CF's closure in this case. Okay, so for the CF, so we initially start with CF, okay? Then we just say which functional dependency here, whose left-hand side contains C or F or both. And then I think AB is not in the CF. BC, only C, but B is not in the CF. So no, D is not in the CF. Now we have CF determines B. So that means that we can apply CF determines B, this functional dependency, then we get B. So add B into the closure using CF determines B. Okay? So we start with CF, then we can add B to the closure because of functional dependency. CF determines B. Now we have CFB. Okay? Then let's see. Okay, so we have a BC determines AD. Okay, so that's AB cannot be applied. D cannot be applied, but BC determines AD can be applied. So that's why we apply BC determines AD. So we're going to add AD to the CFB. Okay, based on this rule. Okay, we add the dependent to the closure. Now we have CFBAD. Okay, now we're not done yet because now we keep examining the functional dependency. We can tell that at least the D, we can apply D determines E because now we have D. Okay, so that means that we can add an E to the closure using D determines E. Okay, so this is a kind of a this is what we got till now. So can we apply any other functional dependency? I think we probably can stop because as of now, we contains all attributes of A, B, C, D. So we have A, B, C, D, E, F. So all 6 attributes. So that actually means that because CF's closure contains every attribute of R, then CF together can be the key of, it has to be a key of R. Okay? So that's kind of a conclusion because the closure of CF contains every attribute of the relation schema. That means that it can be key. So why it can be key? Because given CF, we are able to determine the A's value, B's value, and the D's value and the E's value. So that's kind of a default functional dependency, means that a key determines all other attributes of the relation schema. So that's why CF can be a key. Okay. So this is a way for us to identify a key of a relation schema using the functional dependency. Okay, so we just try to examine, I think we can examine every subset of attributes in the relation schema, examine their closure, and then to identify which closure contains all attributes. But sometimes, once we have this closure CF, we also make sure that CF is minimal. Okay, so if it's minimal, then it's a key. Sometimes we may end up a set of attributes whose closure contains every attribute in the relation, but that set of attributes is not minimal, means that we can remove some attributes from the set, then the remaining set's closure still cover every attribute in the relation. So we have to examine the minimality of the set to make sure that it is minimal. If it is minimal, then this set of attributes is considered as a key. I think here C and F should be minimal because C alone cannot be derive any all attributes in the. Maybe I can copy this one. It's going to be easier. So one way we can do that, we simply just examine if C's closure, so C is the subset of CF, if C's closure contains everything, okay? Okay, so for the C's closure, if we looking for every attributes, every single functional dependency, none of them has the determinant as C, okay? So that means that C's closure will be itself, will be C, nothing else, okay? Then let's look at the F's closure, okay? So the F, I think the same thing. So if you look at this every single functional dependency, none of them has F as their dependent. Although we do have last one like CF, but it means that C and F determines B. So F itself cannot determine B. So that's why the F's closure will be F itself, okay? So that's basically validate that C and F is minimal set of attributes that can derive all attributes of the relation R, okay? Similarly, we can calculate the A's closure. So I think for A's closure is still A because none of the functional dependency has determinant as A, okay? How about the B? B is also, I think the same thing. B is also cannot determine any other thing. So B's closure will be B itself. How about the D? Okay, now D is a little bit different because we do have one functional dependency that has left-hand set determinant as D. So that means that this closure will contain at least E, okay? Then we're going to see if there's any functional dependency whose left-hand set is either D and E or D or E. Unfortunately, no. So that means that this closure will be DE, okay? So then you're probably asking, how about we try the BC? So I think, okay, we do the AB, okay? So then I think we examine the none of the single attribute can whose closure can cover every attributes of the relation schema. Then we think about how about the other attributes. So we probably start as BC, okay? Okay, for the BC, so we initialize its closure as B and C. Then we're going to see if there's any functional dependency that have the either B or C as left-hand side or both. So I think in this case, we don't have B, single B as left-hand side. We don't have single C as left-hand side of those functional dependency. But we do have one BC determines AD. So the BC as left-hand side, okay? So that means that we can further calculate the closure. So the new closure will be B, C, and then because of BC determines AD, so we also going to add A and D, okay? That is using BC determines AD. Okay, so now let me see if I'm able to. Now we have BCAD. Now we're going to examine that if any functional dependency whose determinant on the left-hand side is included in the BCAD. So I think at least AB determines C is 1, and BC determines AD, we have already used it. How about the D determines C? Should be 1. Okay. So since AB determines C, so we have AB in the closure and the C also in the closure. So even we can apply AB determines C, but this will not change. Okay. So I just want to let you know that if we try to apply the functional dependency, AB determines C. So given this closure, I mean the attributes in the closure, even we trying to apply AB determines C, because AB is in the set closure, and all things C is also inside it. So that means that even we add C to the closure, then we remove the redundant attributes. So that means the closure will not change. Then we can also do the D determines E. Okay. So because D is in the BCAD. So if we apply D determines E, we're going to add E into the closure. Okay. Now I think B, C, A, D, E, and I think we applied AB determines C, BC determines A, D, D determines E. The only one left we didn't apply is CF determines B, but we don't have F here. Okay, so that means that we should stop here. So that means that the closure of BC will be the BCADE, but without F. Since BCADE does not have F, that means that the BC together cannot serve as a key for the relation schema. Okay? Okay, questions? I know in the past, I do have students who somehow have difficulty understanding how to calculate the closure. So that's why I have second example in the slide to just show you how to calculate the closure again. So in this example, we have a little bit larger relation schema. So we have A, B, C, D, E, F, G, 7 columns. Then we also see the set of functional dependency. A determines BC, BC determines D, D determines F, and CF determines G. Okay. So then let's calculate the closure of A. So we start initialize closure of A as A. Then we examine if there's any functional dependency whose determinant is A. So we can tell that A determines BC is the one. So that's why we apply A determines BC. Then using A determines BC, we know that start with A. Because of this functional dependency, we're able to derive B and C's value. So we put the dependent to the closure. Now we have A, B, C, okay? Now we're going to examine again to see if there's any functional dependency in the list whose left-hand side or determinant is included A, B, C. So I think we have B, C. So D is not, CF is not, because we don't have F in A, B, C. So we only have B, C that in the original closure A, B, C. So then we're going to apply B, C determines E, okay, D, E. So we're going to add D and E to the closure, okay? So now we have A, B, C, D, E, okay? So we start with A, B, C, then we got A, B, C, D, E because of this functional dependency, okay? Now we reevaluate again. I think sometimes we can cross out, so we know that A determines B, C has been applied already. Can I have a right column? Okay, then we have B, C determines D used. Now we only have two we need to examine. So given the A, B, C, D, E, so given these two functional dependency left, we know that D determines F can be applied because D is included in the closure, okay? However, CF cannot be applied because C is included, but F is not included in the closure. So that's why we can only use D determines F. Then we simply add F to the original set. We end up with A, B, C, D, E, F, okay? So DF is crossed out. Now we have only one left, CF determines D. So we start with A, B, C, D, E, F. So apparently now the closure has both C and F. So that's why we can apply CF determines D, then we update. Means that we put the G to the closure. Now we end up with A, B, C, D, E, F, G, okay? So that's the all seven characters, all seven attributes are included in the A's closure. That means that A can be the primary, can be the key of the R, the relation. Since A has single attribute, so then A by default, a single attribute is by itself minimum. So that's why we can consider A as one candidate key or a key of the relation R. Now it's kind of try to calculate the B's closure. So given all these four functional dependency, none of them has determinant as B. So that's why B's closure will be itself, okay? Let's start with the C. I think the same thing here. So given C, none of the functional dependency whose left-hand side is C. So that means C's closure will be also itself. Okay? Questions? Okay. Let's move on to the next one. How about the closure of D? So it's better for us to put here so we know what are the relation schema. Okay. So D, the closure, none of those, okay, now we do have one, D determines F. So D's closure will be DF, okay? So then once we have DF, I think none of the other functional dependency contains DF on the, as left-hand side or as determinant. So that's why D's closure will be only two attributes, D and F. How about the BC's closure? So BC's closure, we start closure as BC. Then we examine if there's any functional dependency whose determinant is BC, then we do have one. BC determines DE. So we apply BC determines DE. We have BC, DE, okay? Now we're going to examine the remaining functional dependency. We have A determines BC, D determines F, and then CF determines G. I think, yes, we do have D. So I think here, basically, you can apply this functional dependency in the different order. You can apply D determines F in the beginning, and then BC determines D in second. So I think in this case, it doesn't matter, okay? So means that given the BCD, we're able to apply I'm sorry. I think I have to take back. I think I read it wrong. So we have to apply the BC determines DE first. Then we got BCD. Then we can apply D determines F to get closure BCD and F. Okay. Now we can also apply the CF determines G. Okay, so because we have C and F here, so apply the CF determines G, we add the G into the closure. Now we have B, C, D, E, F, G. So that's the closure of the BC. Unfortunately, the closure does not contain all the attributes of R. So I think we miss A. So that's why BC's closure cannot be a key. Okay, so that's what I want you to be aware of that. Okay. Then you may think, okay, if we add A to the BC, so if we try the ABC, I want to leave this for you. So how about the AB? Sorry, I think I don't want to retype this superscript. So I just copy paste, okay? So how about ABC, the closure? So I can tell you that the ABC's closure will contain all attributes of the ABCDEFG. So then it means that ABC's closure contains all attributes of the relation schema R, but we have to also make sure that ABC is the smallest set of the attributes whose closure contains every attribute in the relation R. So if no, then ABC can only be the superkey because its closure contains every attribute. Since it is not minimal, then it cannot be the key. So we have to examine it, okay? So I think according to the original, we have, let me see. So in order to evaluate if ABC is minimal, you probably can try, we do the BC, we can do the AB closure, we can do the AC's closure, and then to see if any subset of ABC's closure also covers all attributes in the R. So we have to get the subset of ABC. So I think its individual attributes closure definitely will not be will not derive all attributes in relation R. So that's why we have to use the set of two attributes. So we can use AB, we can use BC and AC. So we have two set attributes. Then we three sets that contains two attributes, I think. Then you're going to examine the closure of those three sets and then to see if they cover all the attributes in the relation schema. I will leave this for you, and you need to do it to verify if the ABC closure is the superkey or ABC is a superkey or a key. So I think we can discuss this in the next class, okay? So here shows a real-world application of the closure, and this just simply try to identify the key, okay? So given a relation schema, car sale. So in this car sale, we have a bunch of attributes: car ID, option type, option list price, sale date, and option discounted price. So given those attributes, we don't know which set attribute is key. And luckily, we do have a set of functional dependency like car ID determines sale date, option type determines option list price, and the car ID option type determines option discounted price. So what is the key of the car sales? Okay, so I think given these three, probably we can do it in a quick way. So car ID itself cannot be the key because car ID only determines sale date. Then given the car ID and the sale date, we still not be able to find the functional dependency that help us to derive more attributes. So a function dependency 1 will not give us anything. I mean, based on the functional dependency 1, we can say that car ID is not a key. Then go to the second one. So I think maybe we do more. Do I have a? Let me just copy this one. So we usually start with the functional dependence, the determinant, because that's the way we can see if that functional dependencies determinant can go over several functional dependency to determine all attributes of the relation schema. So in this case, the car ID's closure will be the car ID and the sale date because of functional dependency 1, okay? Okay. So if you want to be more accurate, so we're going to initialize its closure with car ID, okay? Then using FD1, we're able to tell that we can add sale date to the car ID. Okay, so that is 1. And I think that's it. So we won't be able to get any other attributes based on the car ID and the sale date because none of those FD2 and FD3, they have the left-hand side as car ID and sale date. So let's go to the option type. So let me copy so that I do not need to tap the superscript. So we have, now we use FD2, we have option type as the attributes we want to start with. So we calculate option types. Maybe this will be a better notation. So we use curly braces and then use the superscript plus sign to indicate the closure. Okay. So we initialize the closure as option ID. Then we can apply the functional dependency. So in this case, the functional dependency we can apply will be the FD2. Okay. So FD2 tells us, given the option type, we can also get option list price. So it means that start with option price, we can get both option price value, that's by default, and also the option type list price because the function dependencies means that the option list price is dependent on option type value. Okay, that's it. Now I think we start with FD3. So now we have for the FD3 we have 2 attributes on the determinant. So that will be the car ID. Option type. Okay, so we initialized with car ID and option type. Okay, then we apply the functional dependency. Maybe I do. So then we can apply the functional dependency 1. So because car ID is in the closure, okay? So by applying the functional dependency 1, FD1, then we can get sale date. So by apply the using FD2, okay? Also FD1, okay? So because FD1, we start with car ID option type. FD1 shows that car ID determines sale date. So we put sale date to the closure, okay? Now we can apply to what? We can apply to the second FD2. Okay, so for the FD2, it shows that option type determines option list price. Okay, that's using FD2. Maybe have to, I think you're able to view it, so let me make it a little bit smaller. Okay, then I think we're still able, we not apply the FD3 yet, because with the rhythm we pick car ID and option type, because that's the left hand side of the FD3. So then we apply that one. So that one, basically we start with what we have here now. So what we derive now will be the car ID option type, sale date, and option list price. Okay. Then car ID option type determines option discounted price. Using FD3. Now we can apply all functional dependency. Then we get the attributes will be this part. Okay. Let me maybe just. So car ID option type, sale date, option list price, option discounted price. So that's pretty much our attribute in the car sale. So that really means that, so it shows that because we have already demonstrated that the car ID the closure cannot cover our attribute. Option types closure cannot cover our attribute. But car ID and option type together, its closure covers our attributes. So that basically means that, so the conclusions will be the car ID option type is a key of car sale. Okay, so this is how we derive the key of a relation schema based on a set of functional dependency. Questions? So I think in practice, it may not be that straightforward. So you have to examine the functional dependency and then to calculate. So like what we saw here, that, for example, an example, so I think example here. So for example, we have a BC. The closure contains BC, AD, but does not have F. Okay. So then we think, okay, let's add F. Okay, so we BCF. Okay, BCF definitely will cover every attribute in the relation schema, but we do see that CF itself cover everything. Cover the closure covers all the attributes of R. So that means that BCF is not a key, it's a super key, but it does not satisfy the minimal additive constraint. Means that B is redundant. So if we remove B, then CF still the closure still cover every attribute in the relation schema. So that basically means that you can do the try and see which set of attributes whose closure contains every attribute of the schema. Then you have that set of attribute as a candidate, and you're going to examine if it is minimal. If yes, then that set of attribute will be a key. If no, you have to remove the redundant attributes. Okay? So in order to identify the minimal set of attributes whose closure contains every attribute in the schema. So this minimum set can be a key. Okay, so I think that's basic talking about closure. And then I think we still have some time to discuss the constraint. So functional dependency is a property of attributes in the schema. So basically, functional dependency is defined based on the meaning of attributes and also their relationship. Okay, so since it is a constraint, that means that the functional dependency should be always held in the data, so in the table, no matter how table change. So that's kind of a functional dependency constraint. Excuse me. Then we kind of review the concept of the superkey and the key. So superkey means a set of attributes that contains a key, at least a key, and may contain some other attributes besides the key. Okay, so that's why superkey still satisfies the uniqueness constraint because it contains a key, and the key is unique for every record in the table. But the superkey might not satisfy the minimal additive constraint if it contains some actual attributes besides the key. So that's why superkey may not satisfy the minimum additive constraint. So then a key basically satisfies both uniqueness constraint and minimum additive constraint. Okay, so a key is a super key but has one actual constraint. It must be minimal. So the relationship between the key and the super key, I think in the database design, we mainly use key, the concept of key. And the super key mainly just help you to know that which set of attributes will be always unique in the whose value will be always unique for every record in a table. So I think that's the main purpose of defining super key. And the key will be very popularly used in a database design and also used to verify if the data satisfy the key constraint. Okay. So that's, I think we have studied the concept of the super key and the key in the past lectures also. So I want to skip the next one. So then the normal form. So in the database design, normal form is very important. So it utilizes the key information and functional dependency information to certify whether a relation schema meets some requirements. Okay, so it's more like normal form is used to certify the goodness of relation schema based on the information of the functional dependencies and the key information. Normalization is considered as a procedure to apply to a relation schema. So normalization basically, the main purpose of normalization is to split a big relation schema into a set of smaller ones so that the set of smaller ones can preserve all the information in the original big one. So how can we do that? We just simply join the set of smaller schemas, then we can fully recover the original big relation schema with no less or no more tuples in the after the join result. So this is called normalization process. So I think we can cover this one also. So for the definition of the key and attributes, besides that, we also need to understand another one is the prime attribute. Okay, so prime attribute is an attribute that appears in at least one of the key in a relation schema. So recall that a relation schema can have multiple keys. So all of them are called candidate keys. So this candidate means that the candidate for the primary key. Okay, even we have multiple keys, then only one is picked as the primary key. So you can have freedom to pick any key as a primary key. Then the remaining candidate keys will be called secondary keys. So primary key, secondary keys, they all are the keys. So primary key is underlined, secondary keys are not. So different user may pick different keys. So given the same relation schema, if it has multiple keys, then you may have say different relation schema. So one relation schema may be with key 1 underlined at the primary key. The other one may be with key 2 underlined. So anyway, so the choice of the primary key is pretty arbitrary. So it's really not that important, but you have to determine which is the primary key. Then you need to underline it in your schema, okay? But anyway, a prime attribute basically relates to every key. So as long as an attribute appears in at least one of the keys, then this attribute is called prime attribute. Then the non-prime attribute is an attribute that does not appear in any keys. Okay, so means that it does not belong to or related to any keys. Then this attribute is called prime attribute. I think we can see the example here. So assume we have student schema has SSN T number, F name, L name, address. So both SSN and the T number are unique for each student. So that indicates student has two candidate keys. One is SSN, the other one is T number. Okay? Then the prime attributes will be SSN T number. Okay? So because we just simply find all the keys, then we put all the attributes of those keys as prime attribute list. Then for the non-prime attributes, other attributes do not appear in any of those keys. So that's why we have F name, L name, address as non-prime attributes. Okay? So I think I want to stop here. So next class, we're going to finish the normal forms and normalization process. Then I think we are done with the relational data model discussion. The reason I spent quite a long time for the relational data model, because I think that's really important. So you have to understand the basic model concepts and about the constraints, about normal forms, about the primary key and so on, so that I think you have pretty much solid understanding and knowledge in a relational data model. So I think next Tuesday we're going to wrap up the relational data model chapter, and then maybe we will move on to the entity relationship type model. So I think we're going to quickly review that model, and then we will switch to the SQL programming, and then we probably discuss some other relational data model techniques. So also the next class, next week, the class will be the virtual. So I will webcasting the lessons during this period of class, during the designated class time. So I will see you online in the virtual room. So any questions?